Hello viewers, in today's class we are going to discuss yet another important problem from Lagrange Mean Value theorem. So here in this session we are going to prove this important inequality by the application of Lagrange's Mean Value theorem. So we have to prove that x minus 1 over x is less than log of x, which is further less than x minus 1 for all values of x greater than 1. So viewers, we have already discussed a lot of problems related to these type of inequalities in our earlier videos, and here once again we are with a new problem. So before proving this inequality, let us quickly recap the statement of Lagrange's mean value theorem. So the mean value theorem says that if we have a function y is equal to f of x defined in some interval, say a comma b, and if this function is continuous in the interval a comma b, and this function f of x is differentiable or derivable in the open interval a comma b, then there must exist one point or at least one point to C lying between A and B, such that the derivative of this function at this point, that is x is equal to C, is f prime of C, and f prime of C is equal to f of B minus f of A divided by B minus A, right? So this is the statement of Lagrange's mean value theorem, and we are going to use this theorem to prove this important inequality. So to prove this inequality, let us first frame a suitable or appropriate function, right? So let us take a function y is equal to f of x, that is equal to log of x, right? And let us define this function in the interval 1 comma x, right? And we'll first apply the conditions of Lagrange mean value theorem to this function, and then we'll proceed further. So the first condition is the continuity of this function, that is log of x, right? And we know that in the domain of log function, this function, that is ln of x, is continuous in the interval, that is 1 comma x, right? And here x is greater than 1, so log of x is defined for all values of x, and this function is continuous, right? Now the second condition is the log of x is also differentiable, because the derivative, that is f prime of x, is d by dx of log of x, that is 1 over x, right? And 1 over x is defined for all values of x in the interval 1 comma x, right? So we have seen that this function f of x is continuous in the closed interval 1 comma x, and it is also differentiable in the open interval 1 comma x. So these two conditions are satisfied by our function. Now there must exist some point C between A and B. Here A is 1 and B is x, right? So we have C lying between 1 and x such that f prime of C, that is f prime of C, is equal to f of B minus f of A. So we have f of x minus f of 1 divided by x minus 1, right? Now f prime of C can be obtained by replacing this x by C, right? So we have now 1 over C, and here f of x is log of x, and f of 1 is the log of 1, and here we have x minus 1, right? So now we have 1 over c is equal to log of x divided by x minus 1, because log of 1 is equal to 0, right? So now we have this expression. So now to prove this inequality, what we will do, we'll frame two inequalities, right? So the first inequality can be obtained by proceeding, here we have c less than x, right? So we'll start with this inequality. Now c is less than x, so it implies that 1 over c is greater than 1 over x. Now 1 over c can be replaced by this expression, that is a log of x over x minus 1, that is greater than 1 over x, right? Now we can multiply both sides by x minus 1. So we have log of x is greater than x minus 1 over x, right? Now since x is greater than 1, so x minus 1 is always going to be positive, right? So when we multiply both sides by x minus 1, the direction of the inequality remains the same. So we have the first inequality, that is log of x is greater than x minus 1 over x. So let us denote this inequality by inequality number 1. So we have proved this part of this inequality. So now let us frame the second inequality. So for second inequality, what we will do, we'll start with this inequality, that is c is greater than 1, because c is a number which lies between 1 and x, and for this inequality we have used c less than x. Now we'll proceed from 1 less than c, right? So now what we will do, here we'll take the reciprocal of both the sides. So we have 1 over 1, and the direction of the inequality get reversed here. So we have 1 over c, right? So it means 1 over c is less than 1, right? Now replacing 1 over c by log of x divided by x minus 1, and this is less than 1, right? Okay, so now we can multiply both sides by x minus 1, and again x is greater than 1, so x minus 1 is going to be positive, right? So multiplying both sides by x minus 1, we have log of x is less than x minus 1, right? So this x minus 1 goes to the right hand side. So here we have inequality number 2. So viewers, we have now these two inequalities. Now if we combine 1 and 2, so combining 1 and 2, what we will get, we get x minus 1 over x is less than log of x, and log of x is further less than x minus 1, right? And this is our desired inequality. So viewers, whenever we come across with these kind of inequalities in which we have three quantities, then what we usually do, we first frame an inequality considering these two quantities, right? So here we have x minus 1 over x is less than a log of x, and in the second part we take these two quantities, right? That is log of x is less than x minus 1, and then we combine both the inequalities to get what we have to prove.